Hello, let's work through the problems assigned out of section 5.1. So first up, we are given graphs of two functions f of x and g of x. F of x is the pointy one down below, g of x the curvy one up top, and we are asked, based only on these pictures, to evaluate the following. So let's just begin at the first one. Okay, so we are asked in the first problem to find g of f of minus 1. So this symbol means the composition of two functions. It's not the product, remember. By definition, what it means to do is to take f of minus 1 and then plug that value into g. So referring to the pictures, f of x is this one down here. If I plug in x equals -1, that would appear to be a 0. So f of minus 1 is 0. So I'm going to take f of minus 1, which is 0, and plug that into g. So then we can look at the graph of the function g. Now what are we plugging into g? We are plugging in x equals 0. So if I plug in x equals 0, we see that g of 0 equals 6. So g of f of minus 1 is 6. So let's try similarly to find g of f of 0. So g of f of 0 means first compute f of 0 and then plug that into the function g. So looking at the graph of the function f, if I plug in x equals 0, it would appear that f of 0 is equal to -1. So we now need to compute g of -1. Looking at the graph for g, if I plug in -1, we appear to have out a value of y equals 4. So based on this picture, g of -1 equals 4. So overall, g of f of 0, well, f of 0 is -1, and g of -1 is 4, so g of f of 0 is 4. Okay, so quite similarly, if we're asked to compute f of g of -1, the first thing we're going to do is compute g of -1. So referring to the graph, we already actually have it marked. G of -1 is 4. So then we need to take the value of 4 and plug it into the function f. Looking right here, we appear to have that f of 4 is equal to -1. So f of g of -1 would appear to be -1. And finally, f of g of 4. Well, the first thing we need to do is compute g of 4. So g of 4 seems to be spitting out a y value of 3. So then we need to compute f of 3, and f of 3, right there, looks like it's -2. So f of g of 4 overall is -2. Very similarly, we now have to compute the composition of two functions, f of g of 4, g of f of 2, etc. But we don't have graphs, rather we're simply given things to compute here. So the first one, for example, to compute f of g of 4, the first thing we need to do is compute g of 4. So let's look at the expression for g of x. G of x is 5x squared plus 6. So to see what happens when we plug in 4, we're going to do 5 times 4 squared plus 6. 4 squared is 16. 5 times 16 is 80, and 80 plus 6 is 86. So g of 4 is 86. And then what we would compute is what's f of 86? Well, f of x is 8 times whatever you input, and we are inputting 86. And 8 times 86 is 688. Okay. So f of g of 4, 688. Okay, similarly, g of f of 2, the first thing we're going to need to compute is what is f of 2? Well, f of 2 is 8 times 2, which is 16, so then I need to compute what is g of 16. Well, g of 16 is 5 times 16 squared plus 6. 16 squared is 256. 5 times 256 is 1,280. Let me quickly double check that. 256 times 5, I would do 33, 25, 8. Yes, 1,280. Then I need to add the 6, of course, so we end up with 1,286 for g of 16. So that's part B. 1,286 is g of f of 2. Okay, then we'll compute f of 1 and g of 0. What makes these look a little different is that we are not taking the function f and plugging it into the function g, nor are we taking the function g and plugging it into the function f, but rather we're taking one function and plugging it into itself, which is totally fine. You're absolutely allowed to do that. So this is going to be f of 1. Okay, f of 1 is just 8, and f of 8 is 64. Using up here, remember, f of x is 8x. Okay, and g of 0, well, g of 0 is exactly 6, computing 5x squared plus 6 when x equals 0. And g of 6 is going to be exactly 5 times 36 plus 6. 5 times 36 is 180, for a total of 186. Okay, so again, we're just plugging functions into other functions. Sometimes we're plugging them into themselves, which is totally allowable. And in the first problem, we had a graph to work with. Here we just have the algebraic expressions. So this problem is almost identical to the last one. We have algebraic expressions for problems, and we're asked to compute a bunch of compositions. So let's just charge through this quite quickly. So f of g of 4 is going to be f of g of 4. Since g of x is 2x, g of 4 is just 8. And since f of x is 3 root x, f of 8 is 3 root 8. We can simplify this down to 6 root 2. And there we have it. Okay, second up, we have g of f of 2. Well, this is going to be g of f of 2. f of x is 3 root x, so this is just going to be g of 3 root 2. G of x is 2 times x, so this is just 6 root 2, which is exactly the same thing we got out before. Okay, the third one, f of 1, is going to be f of 1. f of x is 3 root x, so f of 1 is just 3 root 1, aka 3. And then f of 3 is going to be 3 root 3. And lastly, g of 0 is going to be g of 0. G of x is 2x, so this is just g of 2 times 0, which is just 0. And we just computed g of 0. G of 0 is 2 times 0, which is 0. So overall, g of 0 is 0. All right, so now we are given two functions, algebraic expressions. F of x is 3x plus 2, g of x is x squared. We're asked to find the composite functions, but we're not plugging in a specific value. So we want to leave the input as the variable x. Okay, we're going to use the same variable that was given for the ones up above. Then we want to state the domain of each function. So f of g of an arbitrary input x. Well, that's f of g of x. What was g of x? G of x was x squared. Now f of x says, okay, referring up above, f of the input is 3 times the input plus 2, regardless of what that input is. So if the input is x squared, f of x squared says 3 times the input plus 2. So here is the function f of g of x. It is 3x squared plus 2. Then we can ask, what's the domain? Well, the domain of the function is whatever real numbers are allowable to be plugged into it. And we have here a polynomial, and the domain for all polynomials is all real numbers. Okay. We discussed polynomials, you recall, back in chapters 3 and 4. So moving on to part B. What is the function g of f if I plug in an arbitrary input x? Well, that will be g of f of x. F of x is exactly 3x plus 2. Now, referring to the function g, g says whatever you input, the output should be that quantity squared. So since I am inputting not just x, but 3x plus 2, g says take that input and square it. And if we expand this out, we get 9x squared plus 12x plus 4. And again, this is a polynomial, which means its domain is all real numbers. Moving on to the third one. So in the third one, again, we're composing a function with itself rather than with a different function, but that's fine. There's no obstruction to doing this. So we're going to compute f of x. This is f of x. On the inside there, f of x is 3x plus 2. What does f say to do to the input? Multiply it by 3, and then add 2. And if we distribute this out, we get 9x plus 8. This is a polynomial. It is linear, so the domain is all real numbers. And lastly, if we compose g of x with itself, we go through exactly the same procedure. Okay, so since g of x is x squared, what we're going to end up doing is computing g of x. That inner parenthesis, g of x is x squared, but g says take the input and square it. So the input now is x squared, so I square that for a net result of x to the fourth, also a polynomial, which means the domain is all real numbers. All right. If we have a hot air balloon, the surface area of the balloon in square meters is given by 4 pi r squared, where r is the radius of the balloon. This is assuming, by the way, the balloon is a perfect sphere. Okay. If the radius is increasing as time passes, according to the function r of t is 2/5 t squared, find the surface area as a function of t. So what we know how to do is we can find the surface area as a function of the radius, as given in the problem here. We can also find the radius as a function of time, as given here, which means as time progresses, I can determine the radius, and once I determine the radius, I can determine the surface area. So as time progresses, I can determine the surface area. This is exactly what compositions of functions are useful for. Okay. So if I plug in a time, the first thing I'm going to do is compute a radius. Once I've computed this radius, I can use it to compute the surface area. So r of t is 2/5 t squared. Now the function s, as given originally, says s of r is 4 pi r squared. The particular letter isn't so important. It just means s of the input quantity equals 4 pi times the input quantity squared. So what is s of 2/5 t squared? It is 4 times pi times that input quantity squared. Once we distribute out that squaring and see everything that's going on, we end up with 16 pi t to the fourth over 25. And this is now s as a function overall of time. We plugged in time and we ended up with the surface area. All right, let's find a difference quotient. Okay, so specifically, a difference quotient is this expression right here. For a function f of x, the difference quotient is f of x plus h minus f of x, all divided by h, provided that h isn't 0, of course. So we're going to compute f of x plus h minus f of x over h, assuming h isn't 0, specifically where f of x is 4x plus 8, pardon me. So my denominator is just h. Okay. F of x that I'm subtracting on the right here is exactly 4x plus 8. Now, what is f of x plus h? It's going to be 4 times the quantity x plus h minus 8, because f of x says take the input, multiply it by 4, and then add 8. Here, my input was not just x, it was x plus h. 4 times the input and then subtract 8. Now all we have to do is distribute various minus signs and 4s. So in the numerator, for example, we have 4x plus 4h minus 8 minus 4x minus 8. Oh, sorry, this was a plus here. Okay, I simply copied it down wrong. This was 4x plus 8, so this should be 4x plus h plus 8. Okay, good. And then this is all over h. In the numerator, observe, we have a 4x and a minus 4x. Those cancel out. We have a plus 8 and a minus 8. Those cancel out. So we have 4h over h, and since h isn't 0, we can cancel this out and just get 4. The difference quotient for this function is exactly 4. Almost identical to the last problem, we're going to compute a difference quotient. However, we have a slightly more complicated problem here. So we're going to compute f of x plus h minus f of x and divide this all by h. However, the function is no longer 4x plus 8 as it was in the previous problem. Now it is x squared minus 8. So first, we have f of x plus h. So we take the input x plus h and square it and then subtract 8, because that is what the function says. Take the input, square it, then subtract 8. Then what we have to do is subtract f of x. Well, f of x is x squared minus 8. These brackets and parentheses that I'm putting in are to avoid errors distributing this minus sign. If I simply wrote, and I see students do this very often, if I just wrote this for my f of x, I wouldn't realize that this minus sign was supposed to distribute across that one as well. Okay, so always err on the side of more parentheses rather than too few. And this is all over h. So now in that first bracket, I'm going to expand out x plus h squared, giving me x squared plus 2xh plus h squared minus 8. Here I just still have my x squared minus 8 all over h. Now let's worry about distributing these minus signs. X squared plus 2xh plus h squared minus 8 minus x squared plus 8. And observe, minus x squared and x squared cancel out. This is all still over h. Minus 8 and plus 8 cancel out, leaving behind 2xh plus h squared over h. And in this numerator, I can factor out an h, leaving behind 2x plus h, which can then be used to cancel the h down in the denominator for a final result of 2x plus h. Okay, another difference quotient. In here, instead of just a linear function that we did 2 problems ago, the 4x plus 8, and not just a simple squaring, the last problem, okay, now we have a general-looking degree 2 polynomial, but we just need to proceed carefully. So f of x plus h is 3 times the quantity x plus h squared minus 5 times the quantity x plus h plus 4. Then I'm going to subtract f of x, 3x squared minus 5x plus 4. And all of that gets divided by h. Okay, so let's expand everything out. Okay, so we end up with 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 4 minus 3x squared minus 5x plus 4 all over h. Okay, I've just skipped ahead a little bit and done all of that expansion in that first term in one step. And now when we distribute that minus sign in the numerator, so we still have 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 4. Then I'm going to have minus 3x squared plus 5x minus 4 all over h. And observe, 3x squared minus 3x squared cancels, minus 5x plus 5x cancels, plus 4 minus 4 cancels. So going back up to the top, what do we have now? Once we get rid of everything we've canceled off there, our denominator is still just h. And what remains is 6xh plus 3h squared minus 5h, which can have an h factored out of it, leaving behind 6x plus 3h minus 5. And now I cancel this h from the denominator for a final result of 6x plus 3h minus 5. These difference quotients are used all the time in calculus. If you go on to take Calculus 1, you'll be computing a lot of different difference quotients when you define something called the derivative of a function.